Welcome to Starry Cosmos. The sun is not going dark. Its light will not falter, and no switch will silence the solar wind. But during the long descent from an active solar maximum, researchers say the most extreme space, weather may cross a surprisingly sharp boundary. They call it a switch-off, a proposed point when the violent, irregular storms associated with powerful coronal mass ejections largely give way to a quieter and more repetitive rhythm. If that boundary is real, the sunspot count at that moment may offer an unusually early clue to the strength of the next solar cycle. Tonight, we will separate that conference stage claim from the machinery already watching the sun. Follow a storm from magnetic field to power transformer, and ask what better prediction can genuinely do to protect a technological world. Dim your lights, settle in, get comfortable, and let us begin. If these quiet journeys help you drift off, hit that like button and subscribe to Starry Cosmos so that the next journey through the vast expanse finds you when you need it. Let us settle into a quiet space now. Allow yourself to relax, breathe deeply, and let your awareness drift towards something vast and ancient. We are surrounded by a silent, expanding universe, and within it, our own sun. A fiery heart pulsing with energy that has shaped everything we know. The rhythms of this star are governed by a cycle, a predictable dance spanning roughly 11 years. It is a pattern tracked meticulously by scientists for decades, a testament to the sun's complex behavior, a magnetic heartbeat echoing across light years. We call it the solar cycle, and within its embrace lies a story of increasing activity, then gradual decline, returning once more to renewed intensity. By 2026, solar cycle 25 remains active, but its smoothed sunspot count has declined from the high recorded in late 2024. However, let us clarify something essential. The scientific community rarely uses the phrase solar maximum 2026 with absolute certainty. NASA and NOAA can identify a maximum period, while the exact peak month remains uncertain until a sustained decline appears in smoothed observations. It is like watching a wave crest before it retreats back into the ocean. You know the peak has passed when the swells begin to diminish. On October 15th of 2024, NASA and NOAA jointly announced that our sun had entered its maximum period. This was not a declaration of a specific peak month, but an acknowledgement that a phase of heightened magnetic activity was underway. The precise moment of that peak, the definitive point where the cycle reaches its highest intensity, can only truly be identified in retrospect. Smoothed data, averaged to reduce short-term fluctuations, can eventually reveal a sustained decline in sunspot activity. Think of it like looking at the ripples on a pond. You see the biggest wave first, but only after the disturbances have subsided do you truly understand the overall pattern. NOAA solar cycle progression data, updated in July 2026, provide that longer view. They show a clear drop in smoothed activity following a significant high in late 2024. The smoothed count reached a late 2024 high and then declined through the available 2025 observations. Yet it is crucial to understand that monthly activity has not completely ceased. Individual solar events, solar flares, coronal mass ejections continue to occur sporadically within this declining phase. These events can still be significant even as their overall frequency changes. The term solar maximum 2026 remains a useful search context, a way to quickly locate information about the period. But it is fundamentally a placeholder, an approximation based on preliminary data and projections. Our understanding of solar cycles continues to evolve through observations from dedicated solar missions, including Parker Solar Probe, the Solar Dynamics Observatory, SOHO, and Stereo. These missions are providing unprecedented detail into the sun's behavior, allowing us to refine our models and improve our predictions with each passing day. Even after the period of peak activity has passed, significant solar storms, the large-scale ejections of plasma and magnetic field, can still occur. These powerful events, driven by complex interactions within the sun's magnetic field, are less frequent in number, but can retain tremendous energy. Their sources remain magnetically complex active regions, and the declining phase does not remove the possibility of an Earth-directed eruption. The reason this matters profoundly relates to our daily lives on Earth. These solar events can disrupt radio communications, damage satellites in orbit, critical for navigation and weather monitoring, and even pose a threat to power grids. That's why space weather forecasting is becoming increasingly vital. Agencies like NOAA diligently monitor the sun's activity and issue warnings when potentially disruptive storms are anticipated, allowing utility companies and other organizations to take protective measures. Strategies designed to mitigate the impact of these solar events on our technological infrastructure. Safeguarding systems that rely on stable electrical grids and reliable satellite communication networks. Remain with me as we continue to explore this fascinating interplay between the sun's behavior and its effects here on Earth. Solar maximum is a period, not a single appointment on a calendar. The peak becomes certain only after the sun has already begun to leave it behind. The sun is a restless giant, constantly shifting its moods, broadcasting flares and coronal mass ejections across the solar system. But beneath that turbulent surface, there exists an intricate rhythm, a cycle of activity that waxes and wanes over decades. Recognizing this is not simply about understanding the sun's behavior. It is about anticipating potential disruptions here on Earth. One approach maps unequal solar cycles onto a common phase, a framework often described as a sun clock. In 2021, Sandra Chapman and colleagues published an astrophysical journal study titled The Sun's Magnetic Hale Cycle and 27-day recurrences in the Geomagnetic Index. It is immediately apparent that individual solar cycles are far from uniform. Observed cycles vary in length and amplitude, rather than following an exact 11-year schedule. Direct comparisons become challenging when these cycles vary so dramatically in their length and intensity, creating a scatter of data that resists easy categorization. Yet within this apparent chaos lies an underlying pattern, one that Chapman's team sought to illuminate through painstaking analysis of historical sunspot records. The key was to find a common ground, a shared timescale upon which to project these disparate cycles. Their solution: a standardized 22-year clock, a concept built on the well-established Hale cycle. This clock preserves the alternating polarity of consecutive solar cycles. The global magnetic poles reverse near each solar maximum, while a full return to the original magnetic orientation takes roughly 22 years. It is a fundamental property of our nearest star, and one that provides an invaluable anchor for understanding its fluctuating activity. The analysis maps the daily sunspot number record, available from 1818 onward, onto this standardized cycle phase. This was not about imposing a single metric. It was about creating a framework where individual cycles could be visualized together, their variations rendered as predictable shifts across the clock face. The beauty of this method lies in its ability to reveal subtle transitions within solar activity. They then examined the long-Ah geomagnetic index, which summarizes global geomagnetic activity from calibrated observatory measurements. It records magnetic disturbance at Earth from changing solar wind conditions, including CME-driven storms and recurring high-speed streams. By comparing these measurements with the phase timing derived from the sun clock, researchers could track changes in geomagnetic behavior with remarkable precision. What they discovered was truly fascinating. The transition from a maximum-like disorder, periods of heightened activity, to a more recurrent declining phase does not always unfold gradually. Instead, it can occur within remarkably short timescales. Their research revealed that these shifts can manifest as quickly as a few 27-day solar rotations, a blink in astronomical terms, but an astonishingly rapid change when considering the enormous scale involved. This established work does not predict individual events. It describes how geomagnetic recurrence changes with standardized solar cycle phase. In the 2021 analysis, the transition in geomagnetic recurrence occurs within only a few solar rotations, rather than fading uniformly across the declining phase. It does not, by itself, validate the new precursor proposed for future solar cycle 26. Instead, it provides a sophisticated tool for monitoring ongoing activity and refining our understanding of how the sun's magnetic field dynamically rearranges itself over time. Considering the potential impacts on Earth, these detailed observations become profoundly important. The space weather events represented in geomagnetic records can disrupt communications power grids, and satellite operations, making reliable warnings operationally important. Researchers continue to explore methods for improving these predictions. Building upon this foundational work and leveraging increasingly sophisticated models of the sun's complex magnetic field. As we gaze at the sun's chaotic beauty, remember that beneath the surface lies a delicate clock, ticking silently and influencing our world in ways we are only beginning to fully understand. The clock does not make the sun regular. It gives irregular cycles a shared coordinate. So transitions hidden by unequal years can be compared. Let us consider a proposition that has begun to circulate amongst solar physicists, a potential marker for an impending shift within our sun's activity, one that may subtly reshape our understanding of the coming solar cycle. In July of 2026, at the Royal Astronomical Society's National Astronomy meeting in Birmingham, a presentation titled "A New Declining Phase Precursor" to predict the next solar maximum sunspot number outlined what is currently being described as conference stage research concerning this possibility. The release itself offers no linked paper, preprint, DOI, or fully assembled author list, presenting instead a snapshot of findings developed through ongoing analysis and observation. It is important to recognize that this remains an evolving idea, subject to further scrutiny and revision as more data accumulates. The core concept revolves around the possibility of a solar switch-off, a term used to describe a period where the most extreme coronal mass ejections, events capable of disrupting technological systems here on Earth, become significantly less frequent and intense. It is not, however, an indication that all solar activity or magnetic disturbances entirely cease. Rather, it represents a subtle recalibration within the sun's dynamic behavior. This hypothesized boundary aligns closely with the movement of active sunspot regions below approximately 15 degrees of solar latitude. It is a region where scientists suspect the sun's differential rotation, the tendency for different parts of the star to spin at slightly varying speeds, begins to weaken, fundamentally altering how magnetic fields are generated and released. In the analysis described by the Royal Astronomical Society, storms after this boundary were less extreme and showed stronger recurrence near the sun's roughly 27-day rotation period in the geomagnetic index. This is not a simple proportionality. It is an indication that the underlying mechanisms governing space, weather, are shifting, becoming more attuned to the internal rhythm of our star. Professor Sandra Chapman proposes a relationship between the sunspot number observed at this boundary and the maximum reached during the following solar cycle. Her preliminary estimate places the maximum of cycle 26 around 100 to 120 sunspots. But the switch-off count needed to refine that estimate has not yet been observed. This is not a precise prediction of individual storm dates or a guarantee of any specific intensity, but rather an early attempt to forecast the overall strength of the upcoming cycle. It is critically important to understand that the current estimate for cycle 26, the one anticipated to follow this proposed transition, is provisional. It is a starting point, subject to considerable refinement as observations accumulate and our understanding of these complex solar processes improves. The data from cycle 25 will undoubtedly play a vital role in solidifying or revising these initial projections, providing a clearer picture of how the sun's behavior might evolve over the next few years. The implications for space weather forecasting are significant. If the relationship proves consistent, it could add lead time to broad planning assumptions about the next cycle's activity, while event-specific protection would still depend on operational forecasts and measurements. However, the scope of this predictive capability is necessarily limited. It is not intended to warn of individual solar storms, but to estimate the overall strength of the next solar cycle. Essentially, it offers a 6 to 7 year forecast of cycle strength, a window into what might be expected, rather than an accurate depiction of specific storm dates or fleeting fluctuations. Considering the inherent complexities of our star's behavior, this represents a nuanced but potentially crucial step toward improving our ability to anticipate and mitigate the impacts of solar activity on life here on Earth. The ongoing investigation continues, driven by a deep fascination with the sun's enigmatic dance and a commitment to deciphering its ever-changing patterns. The phrase 7 years early describes a forecast of the next cycle's overall strength. It does not describe 7 years of warning before a particular storm. For now, the precursor is a scientific proposal presented at a conference, not an operational NOAA forecast product. Consider the way sunlight touches your skin, a familiar warmth that has sustained life on Earth for millennia. The sun is more than just light. It is a source of immense energy, constantly bathing our planet with radiation, a constant interplay of forces you might not fully grasp. The same magnetic activity that makes the sun scientifically compelling can also disturb technology near Earth. The proposed switch-off concerns a transition between types of space, whether during the declining phase, not solar energy shifting away from our planet. At its core, the idea centers around 4 distinct phenomena often grouped together, yet each possessing unique characteristics and travel times. First, there are solar flares, brilliant bursts of electromagnetic radiation released near the sun's surface. These flares are not explosions in the conventional sense. They are releases of energy as magnetic fields rearrange themselves, snapping back from a period of intense instability. And like light itself, this radiation travels at the speed of light, arriving here on Earth within roughly 8 minutes and 20 seconds. Strong flare radiation can alter the ionosphere and produce radio blackouts on Earth's sunlit side within minutes, whether or not a CME follows. Then there is the coronal mass ejection, a truly colossal event. Imagine vast quantities of plasma, along with its tangled magnetic field lines, being hurled outwards from the sun's corona, the outermost layer of its atmosphere. These CMEs are not always directed towards Earth. They can be aimed in any direction, sweeping through space like enormous cosmic winds. Some are relatively minor, barely registering as a blip on our monitors here. Others, however, are immense, containing billions of tons of material and carrying enough energy to drastically alter the magnetic field around our planet. The speed at which a CME travels is incredibly variable. High-speed CMEs, those that are particularly potent and often associated with intense flares, can arrive in as little as 15 or 18 hours after their origin. Slower ones, on the other hand, might take several days to reach Earth, giving us precious, but sometimes insufficient, time to prepare. A fast CME can drive a shock through the surrounding solar wind, and that shock can accelerate energetic particles that create a separate radiation hazard. And what is fascinating is that when a CME-driven shock wave, a disturbance created by the sudden movement of plasma, encounters these charged particles, it can cause them to accelerate dramatically. This creates an additional layer of radiation risk, separate from the initial flare activity. The related hazards can therefore overlap without being physically identical. These events rarely occur in isolation. They often coalesce into something even more profound: a geomagnetic storm. A geomagnetic storm occurs when solar wind, a continuous stream of charged particles emitted by the sun, effectively couples with Earth's magnetosphere, which acts as a protective bubble around our planet. This coupling is strongest when the solar wind magnetic field remains southward, allowing efficient transfer of energy into Earth's magnetosphere. Geomagnetic storms can trigger spectacular auroras, the northern and southern lights, but they also pose significant risks to our technological infrastructure. Power grids can be destabilized, satellite communications can be disrupted, and navigation systems can malfunction. The sources of these storms are varied. High-speed solar wind streams can overtake slower wind and form co-rotating interaction regions. These structures can drive storms that are often less intense than CME storms, but may deposit energy over a longer interval. Scientists are diligently working to improve our ability to predict these events, using instruments like NASA Parker Solar Probe and ESA's Solar Orbiter to gather detailed data about the sun's behavior. To help us understand and categorize these different hazards, NOAA, the National Oceanic and Atmospheric Administration, employs distinct R, S, and G scales. The R scale measures radio blackouts, disruptions to shortwave radio communications. The S scale describes solar radiation storms using the flux of energetic protons measured near Earth. And the G scale quantifies geomagnetic storms, their impact on our technology and infrastructure. Importantly, you will notice that radio blackouts, radiation storms, and geomagnetic storms are not interchangeable. Each reflects a different aspect of the broader solar-wind interaction with Earth. These scales represent a crucial framework for safeguarding ourselves against the potential consequences of the sun's unpredictable activity. A bright flare, a cloud of solar plasma, a burst of energetic particles, and a storm around Earth can belong to one event. They are not the same phenomenon, and they do not arrive on the same clock. The quiet hum of progress, a constant undercurrent to our lives, often masks unseen forces reaching out from the sun. Consider the early days of long-distance communication, the intricate web of telegraph wires stretching across continents. By the mid-19th century, these circuits were not just carrying words. They were also susceptible to whispers from space. Geophysical disturbances carried on invisible electromagnetic tides. These were not dramatic solar flares exactly, but subtle shifts in the Earth's magnetic field that, when interacting with the conducting wires of the telegraph system, could create anomalous currents. Sometimes, these currents built up enough to spark fires along the lines. A reminder that even the most sophisticated technology could be vulnerable to forces beyond our immediate comprehension. It was not apocalyptic, but it was a tangible demonstration of how the solar environment could subtly influence our daily lives, long before we fully understood the mechanisms at play. Moving forward a century or so, in March of 1989, a more direct and profoundly disruptive event unfolded, a significant geomagnetic storm driven by a coronal mass ejection. A vast eruption of plasma from the sun slammed into Earth's magnetosphere. The resulting disturbance was recorded as one of the strongest events of that cycle, and its effects were acutely felt in Quebec, Canada. The Hydro-Quebec system collapsed within seconds, leaving millions of people without power for roughly 9 hours. The same storm was associated with a documented transformer loss, showing that geomagnetic disturbance can produce both system-wide and equipment-level effects. It was not a complete collapse of infrastructure entirely, but it illuminated just how fragile our systems could be when exposed to sudden, powerful space weather. Examining these incidents underscores a core principle: that geomagnetic storms are not merely theoretical hazards. They are demonstrable risks with tangible consequences. The story does not end there. A little over a decade later, in October of 2003, another significant solar event triggered disruptions around the globe. The October 2003 storms produced numerous operational effects, including a documented blackout in Sweden. satellite operations were also affected, with some experiencing temporary communications difficulties. Again, while the scale was different from the 1989 Quebec outage, the impact served as a stark reminder that our reliance on interconnected technological systems makes us vulnerable to events originating far beyond Earth's atmosphere. It highlighted the need for greater awareness and proactive measures, even if only incrementally. During the active phase of solar cycle 25, the Sun produced a potent barrage in May 2024. From May 7th through the 11th, multiple strong solar flares and at least 7 coronal mass ejections traveled toward Earth. When these events converged, they combined into what became a prolonged and exceptionally intense G5 geomagnetic storm, the first at that NOAA level since 2003. The NOAA scale is used to categorize storms based on their severity. A G5 represents an extreme event. Crucially, leading up to this storm, NOAA issued advance warnings about the potential for significant space weather impacts. These notifications provided critical information to grid operators and satellite control teams. Some spacecraft proactively adjusted their configurations, shifting instruments into safer modes, anticipating the arrival of disturbed particles. This illustrates that while we cannot predict every solar event with perfect precision, our ability to prepare has advanced considerably over time. The monitoring systems, coupled with predictive models, offer a degree of foresight that was simply unavailable in previous generations. However, it is essential to temper this progress with perspective. The historic storms, the telegraph fires, the Quebec blackout, the 2003 disruptions demonstrate real vulnerabilities and tangible risks. They show us how a powerful space weather event can disrupt critical infrastructure, yet they do not represent evidence of inevitable global civilization collapse, as some sensationalized forecasts might suggest. Each event highlights localized impacts and specific failures, rather than systemic breakdowns on a planetary scale. There is a crucial difference between recognizing vulnerability and assuming catastrophic outcome. Continuing to build more resilient systems alongside enhanced forecasting capabilities remains the most prudent path forward. A measured response grounded in understanding, not fear. Aurora is the visible edge of a much larger electrical event, the same changing magnetic environment that paints the sky can drive current through conductors on the ground. Let us consider now how a magnetic storm can enter and indeed influence our electrical grid. A system built on invisible currents flowing through wires stretching across continents. It begins with changes high above us, within the very heart of Earth's protective shield, the magnetosphere. Rapid fluctuations in the flow of electrically charged particles, ions and electrons, in the ionosphere and magnetosphere generate shifting magnetic fields. These shifts are not static. They are turbulent, dynamic responses to solar activity, particularly coronal mass ejections from the sun. As these energetic events propagate through space, they trigger complex interactions within our planet's magnetic field, producing a cascade of alterations that ripple down towards Earth's surface. These changes in magnetic orientation and strength immediately induce electric fields below as well. These are called geoelectric fields. The magnitude of this induced electrical potential, the voltage, is rarely uniform across the landscape. It depends critically on the local geology, the composition of the underlying rock, and most importantly, its conductivity. Areas with high water content or conductive minerals like graphite, found in sedimentary rocks near coastlines, will exhibit stronger geoelectric fields than regions dominated by granite or basalt. Think of it like this: a riverbed offers a much more direct path for current flow than a dry mountain pass. Similarly, variations in soil conductivity, ranging from clay-rich soils to drier, sandy ones, create localized differences in the strength of these induced voltages. Now let us trace the pathways through which these electrical currents ultimately connect with our power infrastructure. Long grounded conductors, notably the extensive network of high-voltage transmission lines that carry electricity across nations, effectively provide a route for something akin to a direct connection. These lines, often hundreds of thousands of meters long, are not simply conduits. They are gigantic antennas responding to the Earth's magnetic field. The current does not arrive as a wild rush of solar plasma directly slamming into your household wiring. That is largely a misconception fueled by dramatic imagery. Rather, it is an electrical current induced within these terrestrial conductors through electromagnetic induction. Following Faraday's law, as the magnetic field lines change around the lines, they create circulating currents within the metal wires themselves. The strength of this induced current is not constant either. It varies considerably depending on factors like the length of the conductor and the orientation of its alignment with the fluctuating magnetic field. Furthermore, transformers, those vital components that step up or down voltage levels across power grids, possess cores made of electrically conductive materials. When these cores are subjected to strong geomagnetically induced currents, they can experience something called half-cycle saturation. This occurs because the changing magnetic field induces a current in the core material that is out of sync with the grid's alternating current. Essentially, it is missing a half cycle of the electrical waveform. This sudden shift in core behavior has significant consequences. The forced currents cause increased demand for reactive power. That is, the energy needed to maintain voltage stability. It also generates heat within the transformer, producing harmonic frequencies, unwanted oscillations that can disrupt sensitive equipment. Crucially, It elevates the probability of protective devices, like circuit breakers and fuses, triggering unexpectedly. A system already stressed by these induced currents can then descend into a dangerous state of voltage instability. Equipment begins to overheat, potentially leading to permanent damage, or, in extreme circumstances, a cascading outage affecting large portions of the grid. Fortunately, sophisticated monitoring systems have been developed to assess this risk. The National Oceanic and Atmospheric Administration (NOAA) and the United States Geological Survey (USGS) collaborate through initiatives like GeoTime to produce geoelectric products. Sophisticated models that combine magnetic field observations with detailed maps of Earth's conductivity. By factoring in regional geology, soil type, and other conductive materials, these models estimate how strongly geomagnetically induced currents are likely to propagate through the ground and into the power grid infrastructure. Armed with this knowledge, grid operators can take preventative measures, adjusting voltage levels or temporarily reducing loads, ultimately safeguarding our technological systems from potentially disruptive geomagnetic events. The grid does not catch charged particles from space. A changing magnetic field induces a new current in long conductors already connected to Earth. Consider the sheer scale of space weather. A constant dance of charged particles unleashed from the sun. We've come to rely on forecasts for everything from satellite operations to power grids back home. But predicting precisely when and how hard a solar storm will hit remains an enduring challenge. The core of that difficulty lies in understanding the invisible currents flowing within the sun itself. Specifically, the magnetic field lines that drive these powerful eruptions. Today, we are focusing on why the last magnetic direction matters, a subtle yet crucial piece of the puzzle when it comes to safeguarding Earth from the potentially disruptive effects of coronal mass ejections, or CME. Coronagraph imagery is our primary tool for estimating the initial characteristics of a CME as it bursts forth from the sun. These specialized telescopes essentially block out the bright glare of the solar disk, revealing the faint silhouette of the ejected material. The plasma and magnetic fields flung outward at speeds that can reach millions of miles per hour. From this imagery, forecasters can determine a CME's speed, how wide its angular span is across the sky, and roughly estimate the probability it poses a threat, how likely it is to impact Earth. It is like trying to understand a rushing river by observing just a small glimpse of its surface. But we are getting increasingly detailed snapshots as technology improves. Based on these observations, complex computer models are then propagated outward, simulating how the CME evolves as it travels through space. These simulations are vital in supporting NOAA 3-day geomagnetic outlook, a routine forecast that provides an indication of how likely a geomagnetic storm is to occur and its potential impact on power grids and other technological systems. It is a layered approach, creating a probability landscape across the solar system. However, there remains substantial uncertainty surrounding the arrival time and overall strength of any given CME. CMEs do not simply travel in straight lines. They are dynamic structures, constantly interacting with each other, bending and twisting as they navigate the complex magnetic fields of our solar neighborhood. The orientation, the direction of the embedded magnetic field within a CME is particularly difficult to pin down until it is closer to Earth. And that is where a fundamental principle comes into play. Sustained, southward-pointing magnetic field lines couple most efficiently with Earth's intrinsic magnetic field. That means, generally speaking, when CMEs display a preponderance of southward-oriented fields, they are far more likely to trigger intense geomagnetic storms, those dramatic displays of auroras, and potential disruptions to our technology. It is not a guaranteed connection, of course, but it provides a strong directional cue for forecasters. The decisive magnetic orientation is often not measured directly until the disturbance actually reaches spacecraft sitting near the Sun-Earth L1 point, a gravitationally balanced location between the Sun and Earth. These strategically placed observatories act as sentinels, providing crucial data about the incoming CME state. They can provide roughly 15 to 60 minutes of confirmation regarding direction and intensity before the arrival of the electromagnetic shock that constitutes the actual geomagnetic storm at Earth. This critical window allows for a final refinement of predictions. The entire forecasting process is built on layers of information, each addressing a different time scale and level of detail. Cycle scale probability forecasts offer an overview, indicating whether we are currently in a period of heightened solar activity. A more active sun generally leads to greater storm frequency. Days ahead watches provide increasingly specific predictions, giving advance warnings about potential geomagnetic disturbances. And the minutes ahead measurements at L1 deliver the final critical confirmation, the precise magnetic orientation and intensity as it approaches our planet, ensuring we are prepared for whatever comes next. It is a constant balancing act between observation, modeling, and prediction, always striving to unravel the complexities of space weather and safeguard our technological world. A CME can be visible for days before arrival, yet one of its most consequential properties may remain hidden until an upstream spacecraft touches the magnetic cloud, long before any proposed cycle boundary can be useful. Operators already work with a layered stream of space weather information. These products express probabilities, expected severity, and observed thresholds so that established plans can be matched to current conditions. The National Oceanic and Atmospheric Administration, NOAA, serves as a central hub, issuing a complex web of alerts and forecasts designed specifically for operational users. Watches provide advance notice that storm conditions are possible. Warnings state that a threshold is expected, while alerts report that an observed threshold has been reached. And then there are forecast discussions, detailed analyses incorporating observational data and model predictions, offering nuanced insights into expected trends and potential magnitudes of events. NOAA geoelectric field models combine geomagnetic observations with models of Earth's conductivity to estimate the induction hazard along grounded conductors. But NOAA forecasting is only part of the story. The North American Electric Reliability Corporation, NERC, sets the standards for grid reliability across North America. Specifically, the EOP10 reliability standard outlines requirements for transmission operators and reliability coordinators to develop and maintain robust operational plans designed to ensure continued power delivery during geomagnetic disturbances. They are not suggesting a single action every time a watch is issued. Rather, they are demanding a proactive approach, an acknowledgement that grid stability can be significantly affected by these events. A second reliability standard, TPL7, focuses on vulnerability assessments and planning for benchmark geomagnetic disturbance events. Transmission planners and owners have a responsibility to evaluate how their systems might respond to geomagnetic disturbances of varying magnitudes, essentially testing the limits of resilience while benchmarking against known severe events. These assessments delve into a multitude of factors: the flow of geomagnetically induced currents, GIC, through conductors and transformers, the resulting voltage dips or swells that could compromise equipment operation, and detailed analysis of transformer thermal impacts, considering how heat buildup might lead to failures under stress. Crucially, operators are tasked with creating corrective action plans, outlining precisely what steps will be taken if predefined performance requirements are not met. A scenario where the grid may not maintain its intended frequency or voltage levels. The reality on the ground is often a carefully calibrated dance between preparedness and operational constraints. Depending on local grid conditions, operator responses can vary widely. They might simply increase monitoring efforts, closely tracking system parameters for any signs of distress, or they could actively manage reactive power margins, adjusting power flows to maintain voltage stability during disturbances. In more challenging situations, operators may need to dynamically adjust system topology, rearranging power flows via circuit breakers, and even reconfigure grid transfers to isolate vulnerable sections and prevent cascading outages. Any hardware mitigation or switching action must be selected through system-specific engineering studies and approved operating procedures. Long-range cycle forecasts extend across years and can inform strategic planning, training, and investment. But they cannot identify the date or magnetic orientation of an individual CME. Conversely, event forecasts, short-term predictions focused on specific geomagnetic events, support immediate operational decisions, enabling rapid adjustments as disturbances unfold in real time. It is important to remember that there is not a single, universally prescribed switching action. Grid topology varies dramatically from region to region, and applicable entities operate according to established procedures, reliability requirements, and system conditions. The goal is not to dictate a rigid response, but rather to foster a culture of informed preparedness, driven by data-driven forecasts and underpinned by robust reliability standards. Observing the Earth's magnetic field and anticipating these shifts in solar behavior is an ongoing process, a testament to our increasing understanding of this dynamic interaction between the sun and our planet. Warning time does not protect a transformer by itself. Protection comes from a prepared system, a practiced procedure, and measurements clear enough to justify action. Let us return now to a specific point within the broader discussion: the proposed solar cycle switch-off marker. It is not simply an assertion of impending doom, nor should it be treated as a definitive prediction. Rather, the idea has evolved into something more like a rigorously testable hypothesis, one that demands observation and persistent refinement. The Royal Astronomical Society release reports Chapman's estimate that cycle 25 may reach this proposed boundary around the year 2028. That timing is a projection rather than an observed milestone. It is a target, not a guarantee. What researchers are now striving for is something fundamentally more precise: direct observation at the critical point. Instead of estimating the future sunspot count at the transition, researchers hope to record it when the boundary is observed. This shift towards empirical data offers a much stronger foundation for validating, or conversely, challenging the entire concept. That observation would supply the input used by the proposed precursor relationship. Looking ahead, the potential for more refined forecasting lies in the structure of cycle 26. Chapman's team has offered an early research estimate for cycle 26 and expects to refine it at the proposed switch-off. That estimate can later be compared with the maximum cycle 26 actually reaches. The success or failure of this comparative analysis will significantly shape our understanding of how reliably we can anticipate such dramatic shifts in solar behavior. The mechanisms behind the abrupt transition, the proposed latitude mechanism, are still under intense scrutiny. It proposes that weaker differential rotation below about 15 degrees solar latitude reduces the magnetic twisting associated with the most extreme CME-driven events. The idea is compelling, but it requires rigorous peer-reviewed publication and independent testing to gain wider acceptance within the scientific community. Examining its validity necessitates detailed analysis of large datasets, comparing theoretical models against observed sunspot distributions and the evolution of coronal mass ejections, those powerful blasts of energy released from the sun. Crucially, any investigation into this concept must also address potential alternative explanations. The physical processes governing solar activity are extraordinarily complex, and dismissing simpler, more established models would be premature. Independent review should test how the result depends on event catalogs, geomagnetic indices, cycle mapping choices, and the limited number of well-observed historical cycles. It is important to note that NOAA, the National Oceanic and Atmospheric Administration, currently maintains a solar cycle progression prediction that is specifically tailored to cycle 25. NOAA states that it does not yet produce an operational prediction for cycle 26. This demonstrates that while the concept of a predictable transition holds considerable theoretical promise, it is not necessarily ready for immediate application in operational space weather warnings. Yet, acknowledging and investigating these hypotheses does not diminish their value. A useful area of research, one that actively challenges assumptions and opens new avenues of inquiry, can coexist with uncertainty and need not be presented as a replacement for existing forecasting methods. If validated, the precursor could become one additional tool for estimating the amplitude of a future solar cycle. It is about adding layers of understanding, testing boundaries, and continually refining our ability to anticipate the sun's unpredictable dance across the sky. Always observing, always learning, always seeking that elusive predictability within chaos. The next decisive chapter is not written in a headline. It will be written in observations taken when cycle 25 reaches the proposed boundary, and in whether cycle 26 later behaves as predicted. The sun's steady energy shapes Earth's climate and seasons, while its changing magnetic activity can paint the night sky with aurora. For millennia, humans have gazed upon this fiery giant, seeking to understand its power and predict its moods. Now, scientists are proposing a new way to perceive solar activity, a switch-off marker, a subtle shift in the sun's behavior that could refine our long-range forecasts of future solar cycles. It is not about anticipating a sudden, catastrophic silence. Rather, it represents an adjustment in how frequently and intensely the sun might unleash its energy. This observation aims to give us a more nuanced understanding of the rhythms governing our nearest star, allowing for greater confidence in projecting years and decades ahead. The solar system itself provides valuable insights through observations from dedicated space weather observatories. Dedicated missions observe different parts of the system. SOHO and the Solar Dynamics Observatory monitor the sun, while Parker Solar Probe samples the near-sun environment during its close approaches. Measurements of a coronal mass ejection's speed, width, and direction can be fed into propagation models that estimate whether and when it may reach Earth. These models retain substantial uncertainty, but they can support event-specific outlooks over the following days. Closer to Earth, spacecraft stationed near the Sun-Earth L1 point sample solar wind speed, density, and magnetic field direction. Those upstream measurements can confirm the arrival and magnetic character of a disturbance roughly 15 to 60 minutes before it reaches Earth. As space weather intensifies, ground-based instruments play a vital role in localized hazard assessment. Magnetometers positioned around the globe measure rapid changes in Earth's magnetic field during a geomagnetic disturbance. Earth conductivity models, combined with magnetometer data, estimate regional geoelectric fields and the induction hazard to long conductors. Simultaneously, grid sensors embedded within power distribution networks detect changes in voltage and current flow that signal potential disruptions. This layering of observation allows scientists to hone in on the precise location and severity of a hazard as it continues to develop, offering increasingly refined warning times. This stream of data supports tangible action through operating plans and reliability standards, including those maintained by NERC for the North American Bulk Power System. These standards are built upon the scientific information gathered, inspiring a new approach to planning, developing detailed procedures for mitigating risk, conducting comprehensive assessments of infrastructure vulnerabilities, and establishing corrective actions designed to minimize impact. Every protocol, every safeguard is rooted in our understanding of how the sun behaves and what it can unleash. It is important to acknowledge that no forecast prevents the sun from erupting. It simply provides a window into potential consequences. No single product guarantees that these impacts will be avoided entirely. The sun has an inherent unpredictability woven into its very nature, a testament to the complexity of our solar system. However, there is a deeper truth here. Resilience is not about eliminating risk entirely. It is about recognizing the difference between anticipating and preventing. The key lies in matching each warning timescale, from the broad cycles spanning decades to the immediate flares measured in minutes, to the decisions it can honestly support. A long-range prediction, while valuable for strategic planning, does not dictate the necessary response when a strong CME is imminent. Similarly, an alert about a potential geomagnetic storm informs adjustments to satellite operations, but should not trigger widespread panic or system-wide shutdowns. It is a continuous calibration, a partnership between scientific observation and informed action. As we continue to listen across every timescale, to the whispers of solar cycles, the surges of space weather events, and the subtle shifts in Earth's magnetic field, we move toward a more secure future, not one shielded from the sun's power, but profoundly equipped to navigate its dance with our world. The sun does not need to become harmless for civilization to become more resilient. We need to hear each signal early enough, understand what it means, and refuse to claim more certainty than it contains. The sun never truly goes silent. Even in quieter years, particles and magnetic fields continue to move across the space between worlds. What may switch off is narrower and more subtle. One regime of extreme, irregular space weather, visible only when many solar cycles are placed on the same clock. That proposed marker still has to survive publication, testing, and the arrival of solar cycle 25 at the predicted boundary. It cannot tell an operator which transformer will be threatened 7 years from now. But long-range cycle outlooks, days ahead storm watches, and minutes ahead measurements each answer a different part of the same problem. Civilization is not protected by one miraculous signal. It is protected by observing early, stating uncertainty clearly, and knowing what to do when the warning arrives. Thank you for spending this time among the stars with me. If you enjoyed the journey, a gentle like and a subscribe help more quiet dreamers find their way here. Until next time, rest well and keep wondering about the cosmos. Good night.